We're going to solve some more examples in order to review the rolling motion. The first one is the following. A plank with a mass M, 6 kg, rests on top of two identical solid cylindrical rollers that have radius R and mass small m. The plank is pulled by a constant horizontal force F applied to the end of the plank and perpendicular to the axis of the cylinders, which are parallel. The cylinders roll without slipping on a flat surface. There is also no slipping between the cylinders and the plank. Find the initial acceleration of the plank at the moment the rollers are equidistant from the ends of the plank. Find the rollers at this moment and what friction forces are acting at this moment. Okay, first of all, I would like to say that because I'm trying to move the plank to the right and the cylindrical rollers will resist this motion and they will apply exactly the same force of friction, the plank is going to feel a friction force to the left of amount 2F. The corresponding friction that is going to appear at the top point of the cylindrical rollers will be F each, so small f each, force of friction to the right. Now for the bottom surface, since this is rolling without slipping, I have no idea where the force of friction points, so I just will assume it's going to be pointing to the right, and Newton's laws of motion will be if I was right or wrong. Okay, now I want to start solving the problem by looking at what's happening to the plank. So for the plank, net force acting in the positive x direction will be given by the capital F that we're applying minus two friction forces that are appearing at the top points of the cylindrical rollers interface with the plank. And this is going to give me the mass of the plank, capital M, times the acceleration of the plank, which is equal to mass of the plank times acceleration of the top points. So let's call the top points T here. So top point is T, bottom point is B. Okay, so then it's going to be mass times acceleration of the top point. Now, I would like to know how this motion, the top acceleration is related to the angular acceleration of the rolling without slipping. For that, I have to remember what happens in rolling without slipping. If this is rolling with angular speed omega, I know that the center of mass velocity has to be equal to omega times r, and the top point t will have a velocity, v top will be omega times r plus velocity of center of mass. Rotation plus translation of the center of mass, it's 2 omega times r, and acceleration at the top is 2 alpha times r. It's just taking one derivative. Acceleration of the center of mass is alpha times r. So what I have called a top here is actually equal to 2 alpha r. So let's keep this in mind. That comes from rolling without slipping. And F minus, capital F minus 2F is mass times acceleration of the top. So that gives me, these two equations give me F, capital F minus 2F is equal to 2m alpha times r. So let's keep this equation in a box. Now I would like to get another equation that relates force of friction to alpha. And for that, because I have two unknown forces of friction, I would like to eliminate one of them. So I'm just going to look at the torque with respect to the bottom point. Okay, because there will be no contribution from force of friction F prime for the torque around the bottom point. So torque with respect to point B. And what is that torque? It is R cross F. It's going to cause a rotation that's clockwise. So let me show this with red here. So that corresponds to the torque due to the F, small f. So it is small f times 2r is equal to moment of inertia for rotations around point B times alpha. That's the torque equation. And at this point, I see that it's a cylindrical roller. So for rotations around the central axis, I have moment of inertia is equal to mr squared over 2. So I recall this from previous examples. And therefore, but this is small mr squared over 2 because that's the mass of the cylinder. The moment of inertia for point B is small m r squared over 2 plus small m r squared, because that's the distance between the two axes. This is r, so I have to add plus mr squared. So this is 3 over 2 small m r squared. So that gives me, for the torque equation, small f times 2r is equal to 3 over 2 small m r squared alpha. One of the r's disappear. So I find that f is 3m r alpha divided by 4. So if I substitute this result into my previous equation, so I have obtained force of friction in terms of alpha, I can substitute it here. What will happen? Capital F minus 2 small f, 3 mr alpha divided by 2 is equal to 2m r alpha. So that means I can solve for alpha from this equation. F is equal to alpha times 2 capital M R plus 3 over 2 m small m r. Okay, so alpha is equal to so I can change this to 4mr over 2. So it will be 2f divided by r times 4 capital M plus 3 small m. So that will be alpha. Then what will be the acceleration, initial acceleration of the Planck? That's the top acceleration, that is 2 alpha r. So it will be equal to 4f divided by 4 capital M plus 3 small m. So this will be the acceleration of the initial acceleration of the Planck. Find the acceleration of the rollers at this moment. Acceleration of the rollers, probably it's asking the acceleration of the center of mass. Acceleration of the center of mass is alpha r, so it will be half of this result, so it will be 2f divided by 4 capital M plus 3 small m for each cylinder. And finally, what friction forces are acting at this moment? Since I know alpha, I can figure out what small f is. Small f is equal to 3mr over 4 times alpha, which is 2f over r, 4m plus 3m. So these r's will cancel. This 2 will give me a 2 here. So it's going to be equal to 3fm over 8m plus 6m. And let's get this in right units. So let's divide it by small m. So this will be 3f 8m over m plus 6. I have divided top and bottom with m to make sure that I have the unit of force here. So this will be my force of friction, F. How am I going to find F prime? I can look at a roller. So for a roller, I have two forces. F plus F prime is equal to mass times acceleration of the center of mass. Now I have to be careful about the relationship between alpha and acceleration of the center of mass. So if this rolls like this, so that's what I have assumed, the acceleration of the center of mass will be in the positive direction. So here I can substitute alpha times r for acceleration of center of mass. So this is equal to 2m f over 4m plus 3m. So f prime will be equal to 2mf over 4m plus 3m minus f, which is 3mf over 8m plus 6m. So if I multiply this one by 2 over 2, I will get f prime is equal to 4 minus 3, 1mf over 8m plus 6m. So that will be the answer for this one. And it will be to the right, so my assumption was correct. I've got a positive answer for this one, so it will be acting to the right. So this is to the right, this is to the right. Okay, I hope it's clear. So if you wish, you can substitute the numbers and you can get the numerical result easily, which is done in the lecture notes. So I'm going to move on to the next problem. A common demonstration illustrated in figure consists of a ball resting at one end of a uniform board of length L that is hinged at the other end and elevated at an angle theta. A light cup is attached to the board at a distance RC so that it will catch the ball when the support stick is removed suddenly. Show that the ball will lag behind the falling board when theta is less than 35.3 degrees. assuming the board is 1 meter long and is supported at this limiting angle, show that the cup must be 18.4 centimeters from the moving end. So first of all, we need to understand what will happen here. This support stick will be removed, so this ball will start falling, and at the same time this stick uniform board will start rotating, and we would like the cup to end up here so that it will catch the ball. Okay, so that's the idea of the problem. Now, when I remove the support stick, I would like to know what will be the torque acting on this. So let me draw here. I have the angle theta. This is a uniform board. So here it's a uniform board. So the center of mass is right in the middle. So it's going to have a weight mg. So let's call the mass m here. And therefore it will have a component that is perpendicular to the board at a distance L/2 from its end. Because the cup is light, we can neglect its torque. The mass is negligible, very, very small. So I'm going to assume that the net torque acting on this is going to come from the weight of the board. So here is the vector r that connects the pivot point to the point of application of the force. So I'm going to have L/2 times mg cosine theta, the perpendicular component of the weight. So that will be my torque. So this is going to give me moment of inertia times alpha. Now, for a uniform board with length L, for rotations around one end, what is the moment of inertia? The moment of inertia is, for this point P, ml squared over 3. That you can recall from previous problems. So I have mg L/2 cosine theta is equal to ml squared over 3 alpha. So m's disappear, one of the l's cancel. So I find that alpha is 3g cosine theta divided by 2l. And so if I go back to the statement of the problem, it says show that the ball will lag behind the falling board when theta is less than 35.3. So that means they're not coming down with the same acceleration. Okay, so what will be the tangential acceleration, or what will be the acceleration of the cup? The tangential acceleration of the cup when it starts falling is equal to alpha times rc for rotation, because this is going to be a rotation. So this will be 3g rc cosine theta divided by 2l. Now, if the ball will lag behind the cup, I need to look at the component of this acceleration that is on the vertical axis. So that is on this axis. So this angle is theta. So I have acceleration of the cup y component is 3grc cosine square theta divided by 2l. Okay, so I take its projection to the y-axis, And when is this acceleration exactly equal to g, then that means they are falling down with the same acceleration, so nobody will lag behind. But if you want the ball to lag behind, I want this acceleration to be greater than g, right? So if it's greater than g, what is g? Acceleration of the ball is going to be equal to g. So I will find that cosine square theta should be greater than 2L divided by 3RC. Okay. Now, it actually says show that the ball will lag behind the falling board, not the cup. Okay, so it's not actually RC, it is, so I'm not concerned about the cup here. What I'm really concerned about is the end of this board. So it will lag behind the board. So we should read the problem more carefully. The ball will lag behind the falling board. It doesn't say the cup. So it is the top point of the board that I'm considering. So acceleration of the top point, so let me delete this one here, will be the tangential acceleration, which will have a component given by a multiplication with cosine theta. So this will be equal to alpha times L, that's the tangential component, and I will have for this one 3g over 2L cosine theta times L, so the L's will cancel. And then if I take the y component of this one, so this will be 3g over 2 cosine square theta. And I want this acceleration, that's this component, to be greater than g. So that means I want cosine square theta to be greater than 2 over 3. So when is cosine square theta 2 over 3? You can calculate this. This corresponds to theta equals to 35.3 degrees. So for theta less than 35.3 degrees, this acceleration of the top point will be greater than acceleration of the ball. Y component will be greater than the acceleration of the ball. So it will fall with higher acceleration. It will speed up faster. Now it says, let's assume that the board is 1 meter long and is supported at its limiting angle. So theta is 35.3. Show that the cup must be 18.4 centimeters from the moving end. Okay, so here is the cup that is at a distance r sub c from the left end, and when it's going to fall, it will come down here so that the ball will fall right into it. Okay, and the total length here was L. This was L. So I have cosine theta is equal to RC divided by L. So RC is L times cosine theta. L is 1 meter. Cosine 35.3. That gives me 1 times cosine 35.3, 0.816 meters. Okay. So what should be the distance from the moving end, the end of the board? That is L minus RC. So 1 minus 0.816 meters. That is 0.0184 meters or 18.4 centimeters from the moving end. So it's this distance L minus RC. Okay, so let's move on to the next problem. Okay, so we have a pulley which doesn't turn. We have a string that is going around it. There is a block of mass m which is coming down with acceleration a, and the string is coming from a spool, let's say, which is a solid cylinder that is rotating and rolling without slipping, obviously, with acceleration capital A. The question is, can we relate small a, the acceleration of the block, to capital A, acceleration of the cylinder? Now, for the block, if I look at the free body diagram, I see I have mg and t, so I simply have mg minus t is equal to ma, the downward acceleration. And for the cylinder, the solid cylinder, I have capital Mg and the tension T, so capital Mg minus T is equal to capital Ma, and because it's rolling without slipping, why is this rolling? Because I have a torque that is coming from the tension. So the torque, so I write the torque with respect to center point of the cylinder. It's going to be equal to T times R, that is I center of mass times alpha. If this is a cylindrical object, what is the moment of inertia? It is capital M R squared over 2. So capital M R squared over 2 alpha. The torque it causes is like this. R cross F is basically pointing into the page, and I'm getting one of the R's cancelled, and alpha, or tension, is equal to mr over 2 alpha. Okay, or in other words, alpha is equal to 2t over mr. Now, what is the relationship between this alpha and small a? Small a is the acceleration of also this point, the left point, let's say. Small a is acceleration of the left point. It's the acceleration of the string, and that is equal to alpha times r, because it's rotating with angular acceleration alpha. So this is equal to alpha times r, and so I can substitute that into the first equation I got here, mg minus t, which is mr over 2 alpha, is equal to ma, which is m alpha r. So I obtain another equation for alpha here. So mg is equal to alpha times mr plus capital MR over 2. Okay, so let's write this in a better way. This is 2mr over 2, 2mg divided by capital MR plus 2mr. That's the angular acceleration. Now, capital mg minus t is equal to ma. Okay, and t is equal to m over 2 times alpha r, so it is actually m over 2 times a. So mg minus m over 2 times a is equal to ma. So these will cancel. I find a is equal to g minus a over 2, which is the question that is being asked in this problem. But I have done some extra things here. I have calculated alpha, so I can also find, if necessary, the tension acting on this string. So tension is mr over 2 times 2mg mr plus 2mr. So the 2's cancel. It's going to be equal to capital M small m g divided by capital M plus 2 small m, because the r's will cancel. So let's demonstrate that here. I have too many r's. They will cancel. So this will be the tension. Okay, but this was the question that was asked. Okay, finally, I have one more example. A uniform solid disk of radius r comes into contact with a rough surface while moving with velocity v0 I hat. Pure translation, the coefficient of kinetic friction is mu k. How long does it take to start rolling without slipping? And I would also like to know what is the final angular speed, what is the final center of mass velocity, and how much work is done on the system by friction in converting this pure translation to rolling without slipping. Okay, so let's look at this case here. I have a smooth surface and then the cylinder will come into contact with the rough surface, and initially it is just moving with v0 velocity, the top point also, the bottom point also. It's just pure translation. And when it comes into contact with this rough surface, it's going to feel a friction, force of friction, which will be kinetic friction opposing the motion, and that is going to give me a torque with respect to the center, and it will eventually turn this into rolling without slipping, so that I will have velocity is equal to omega times omega final times r, and this is rolling with angular speed omega final. So I would like to know how long it takes for this to happen. Okay, so I would like to write the net force on the x-axis. It is force of friction minus mu k mg, mu k times the normal force. That's going to be equal to mass times acceleration of the center of mass. So I see that the center of mass is going to accelerate or decelerate with mu k g, when it comes into contact with this rough surface. Okay, and what will happen is the velocity of the center of mass as a function of time will be v0 minus mu kg, its center of mass acceleration, times t. So that finally it will become equal to omega final times r. That will be its velocity for rolling without slipping. Okay, that's constant acceleration motion. Now, also, I would like to write the torque equation. So the torque with respect to center is Fk times r, that's the torque, mu k mg times r, that's equal to I alpha. Now what is the direction of this torque? It is the direction that I have drawn in the figure. And what is the moment of inertia for a uniform solid disk with radius r? The moment of inertia is mr squared over 2 for a uniform solid disk. So this is mr squared over 2 times alpha, because I'm taking the center of mass as the pivot point here. So this 2 will get rid of one of these r's. The m's will disappear. So I will find that alpha is equal to 2 mu k g over r. Okay, so the angular speed omega will start with omega initial, and then it will increase with alpha times t, but omega initial is 0. So omega as a function of time is 2 mu k g over r times t. So when I reach omega final, when t is equal to t final, I have omega is equal to omega final. Omega final will be 2 mu k g over r t final. So if I go back to this equation, the velocity of the center of mass will be v0 minus mu k g t final, and this will be 2 mu k g t final, so that t final is v0 divided by 3 mu k g. So the time it takes for it to start rolling without slipping is v0 divided by 3 mu k g. What will be omega final? I can just substitute this result here. Omega final will be 2 mu k g over r times v0 divided by 3 mu k g. So omega final will be 2 v0 over 3r. And what will be the final center of mass velocity? V final is omega final times r, so it will be equal to 2v0 divided by 3. And what will be the work done by friction during this process? Okay, so let's do that here. Initial kinetic energy was 1 over 2 mv0 squared. Final kinetic energy is 1 over 2 V center of mass squared plus 1 over 2 I omega squared. So this will be equal to 1 over 2 m 4 V0 squared over 9 plus 1 over 2 m r squared over 2 4 V0 squared over 9 r squared. So the final kinetic energy is let's get rid of one of the 2's here. 4 mv0 squared, the r squareds cancel, plus 2 mv0 squared, 6 mv0 squared divided by 18, so it's m v0 squared over 3. Delta k is 1 over 3, it's k final minus 1 over 2, k initial, m v0 squared, so this will be 2 minus 3 minus 1 over 6, m v0 squared. So this is the energy that has been consumed by friction, that is work done by friction, which means it's the energy, or in other words, energy consumed by friction. So the friction doesn't really do any work, it's just consuming energy, it's converting the mechanical energy into the internal energy of the system, heating up the system. So that's my answer for the last part. The change in kinetic energy is the work done by the acting on the system, which is not a real work. It's